Good evening, everyone. Am I audible?
Yes, you are on.
Yeah. Okay. 1 minute. Okay. So today we will do the problems regarding the week 6. So in the week 6, actually, what are all the things covered? It started with some like isometry. What is isometry? And then orthogonal matrix. And after that, mainly the week 6 is actually for the eigenvalues and the corresponding eigenvector, characteristic equation, and like diagonalizability and all. So we will start with the one or two questions regarding the isometry. Actually, there is nothing much in the isometry, and later on we will go to the eigenvalue, eigenvector, those kind of problems. Okay. So if you have doubt, like in the concept, if you have any doubt, you can ask in between. So we will just start with the questions itself. So the first question, it's a very simple question. Which of the following linear transformations are isometry? So the first one, T is from R2 to R2 such that T of xy equal to minus xy. And the second one is T is from R3 to R3 such that okay. So, what is the definition of isometry or any other equivalent definition? When we will say T is an isometry, one definition is norm of TV equal to norm V. Okay, it's an isometry if for every vector V in a vector space V, capital V, if norm of TV is same as norm of V, then we can say it is an isometry. Okay, so here we will start with the first question. So, what is norm of Txy? Like xy is some random vector in R2. Let xy any arbitrary vector in R2. What is norm of Txy by definition? What is the definition of norm of Txy? It is norm of minus xy. Okay. What is norm of minus xy? How we will define the norm in R2? Square root of the inner product, right? So it will be square root of x square plus y square. That means actually what is this? Not x square plus y square. It is square root of minus x square plus y square. First coordinate is minus x, its square plus y square. But basically it is, what is minus x square? It is x square itself. So this is same as norm of xy. Okay. So we are starting with some point xy in R2 and we found that norm of txy is same as norm of xy. Okay. Is this clear? So T is an isometry. Is this fine for everyone? Any doubt? Is this okay?
Yes, ma'am.
Okay, okay. Actually, this is the one way to find the whether it is an isometry. If we are writing T as in a matrix form also, suppose if I am writing T in a matrix form, what is T of xy? It is equal to minus x y. Okay. How can I write it in the matrix form? I will write T of 1 0 equal to minus 1 0. Correct? This is equal to minus 1 into 1 0 plus 0 into 0 1. In the same way, T of 0 1 is 0 1. That means 0 into 1 0 plus 1 into 0 1. So, the matrix of T with respect to the ordered basis 1 0 0 1, okay, B were equal to minus 1 0 0 1. What is our B here? It is 1 0 0 1. Okay. Now, if we are writing a linear transformation in terms of the matrix form with respect to an ordered basis, standard ordered basis, and if the corresponding columns, either columns or vectors or row, okay, either column vectors or row vectors, we can check if they form say orthonormal basis, uh, or not orthonormal or orthogonal, okay, whatever. Then in that case also we can say T is an isometry. Uh, Here we have minus 1 0 and 0 1. Okay, here this is our column vectors. Column vectors. So if I am taking the dot product minus 1 0 minus 1 0, this is 1, and 0 1 dot 0 1, this is 1, and minus 1 0 dot 0 1. This is equal to 0. Okay. What does this mean? It is an orthonormal set. So, if the column vectors form an orthonormal set, then also we can say T is an isometry. So, this is an equivalent definition. So, if you want to check T is an isometry, either we can go by the definition norm TV equal to norm V, or we can go with this kind of uh, write it in the matrix and check whether the column or the rows forms a orthonormal set. Fine. Now let us go to the second question. Uh, P T of xyz equal to x plus y plus z, x plus z. Now, what is norm T of xyz? It is norm of x plus y plus z, x plus z. Okay, can anyone say what is this value? What is, by definition, what is this norm?
Like the square root of the squares of all the.
Yeah, square root of x plus y square, y plus z square, x plus z square. Now, will it be equal to norm of xyz? What is norm of xyz? It is square root of x square plus y square plus z square. Okay, now is norm txyz and norm xyz are same?
No.
No, need not be. Like for some particular cases it can be. Okay, but in every cases actually we need this condition for all xyz. For example, if I am taking the value 1 1 1 xyz, so what I will get, if this is our xyz, what I will get, norm of t of xyz, it will be 2 2 2, and it will be root of 2 square plus 2 square plus 2 square. At the same time, what is norm of xyz? Here xyz is 1 1 1. Norm of 1 1 1 is root of 1 plus 1 plus 1. So these both are not equal. So T is not an isometry here. Okay. So this is basically, we can see this is not an isometry. No. Okay, now let's go to the next question. So in isometry and orthogonality, we don't have like that much more concept than this. Okay, let's go to the next question. Prove or disprove. Product of two orthogonal matrices is always orthogonal. Okay, so question is to check whether the product of two orthogonal matrices is orthogonal or not. So, what is the definition of an orthogonal matrix? If A is an orthogonal, what is the condition? A is orthogonal if A into A transpose equal to identity, which is same as A transpose into A. Okay, if this condition, that means, what does this actually means? The inverse of A is nothing but the A transpose. Okay, usually what we will write, A into A inverse equal to identity, which is same as A inverse into A. So here instead of A inverse we have A transpose. That means A transpose act as the inverse here. Okay, so if this condition is satisfied, then we will say A is orthogonal. Now can anyone say if let A and B are orthogonal matrix? Now the question is, product AB is an orthogonal matrix or not? Okay, so what we want? AB into AB transpose equal to identity or not? This is the question. Or in the opposite way, AB transpose into AB is identity or not? So we will start with the AB into AB transpose. How can we expand this AB into AB transpose?
AB into B transpose A transpose.
Yes, B transpose A transpose. Okay, AB transpose, whole transpose is B transpose A transpose. Now, from here what we can write next step? Use the condition we already have. What is the condition we are having? A and B are orthogonal matrices. So what we are having? A into A transpose is identity, A transpose A, and B into B is also orthogonal, right? So B will also satisfy this condition. Okay. Now can you say anything? What is the next step?
Yeah, B into B transpose we can replace with I.
Yeah. So we are obtaining A into I into A transpose because we replaced the B transpose with the I. So this is nothing but the A transpose. Again, what is A transpose? Since A is orthogonal, it is again identity, correct? Okay.
Yeah.
So what we are getting, AB into AB whole transpose is identity. Fine. In the same way, we can prove AB transpose into AB. It will come B transpose A transpose A B. Here instead of A transpose A, we can give identity. So we will get B transpose B. It is again identity. Okay. So if A and B are orthogonal, product is also orthogonal. Place AB is an orthogonal matrix. Clear? Now let's go to the next question. Again, prove or disprove. Okay, first question is, see, in the first question, what we got is corresponding to T of xy equal to minus xy, what we are getting is a matrix TB equal to minus 1, 0, 0, 1. It is a diagonal matrix. Okay, it's also a symmetric matrix also. And in the second one, see, if we are writing the matrix of T here, what we will get? We will get 1, 0, 1 and 1, 1, 0, 0, 1, 1. Okay, here it is not diagonal, not symmetric, but we got T is not a like T is not an isometry. In the same way, we can say the corresponding T is not orthogonal. So our question is this true in general? That means if T is a, or if A is a matrix which is orthogonal, is it always diagonal or is it always symmetric? So can anyone say that, like, whether it is true, or can you give a counter example? That means a non-diagonal matrix but which is orthogonal. A non-diagonal orthogonal matrix and a non-symmetric orthogonal matrix. Other than diagonal, how can we find a orthogonal matrix? Okay. So actually both of these are false. Okay. We can find a matrix which is not diagonal but orthogonal, and not symmetric which is orthogonal. So for the first case, I'll give you the example 0, 1, 1, 0. Okay, this is my A. What is A transpose? A transpose is again 0, 1, 1, 0. Here it is not a diagonal matrix, it is an off diagonal matrix. Okay, now we can see A into A transpose is 1, 0, 0, 1, which is equal to identity. Okay, so we got a counter example that is an not a diagonal matrix such that it is a orthogonal. A is orthogonal but not diagonal. Now the next question is this orthogonal matrix, any orthogonal matrix, is symmetric or not? So in the above example also, whatever we got is a non-diagonal but it is symmetric matrix. Now can you find a asymmetric matrix? Means not symmetric matrix. Symmetric in the sense A transpose should be equal to A. Okay, this is symmetric. A matrix A such that it does not satisfy this condition but it should be orthogonal. So I can give a hint such that just modify the above a, whatever we got this a here, okay, just modify this a such that it is not a symmetric metric. Just think 1 or 2 minutes. So if you are not able to find, I'll tell. Any idea? Okay. What will be if I am taking 0 minus 1, 1, 0? Now, what is the A transpose? A transpose is interchanging the rows and columns. So, the first column will become the first row. Okay. The first row of A is the first column of A transpose. So, 0 minus 1, 1, 0. Now, what is A into A transpose? This is 0 into 1, 1, 0, 0, 1. Again, A into A transpose is identity, but A not equal to A transpose. That means A is orthogonal matrix, but it is not symmetric. Okay. So, an orthogonal matrix, actually here we are just changing rows, columns, or like whatever the identity, we are just changing the interchanging row, column, or just multiplying with the minus 1. Those kind of things only we are doing. Actually, an orthogonal matrix can be, in any way it can be complicated also. Complicated in the sense, here we are having so many 1, 0 like that. Other than that also, for example, I will give one matrix A. Take A equal to 1 by 3, 1 minus 2, 2, 2 minus 1 minus 2, 2, 2, 1. Okay, so if we are taking A like this, here we can see that A is not diagonal. It is not very simple matrix, not diagonal, not symmetric also. But you can just verify, you can just do the multiplication and all and verify that A into A transpose is identity. So, A orthogonal. So, orthogonal, like as we think, orthogonal matrix need not be very simple, as we seen already. It can be a bit complicated. It's not so complicated, but something like this also. Okay. Okay, then now we will go to the main section of the last week. So the main section is actually based on the characteristic polynomial eigenvalues and all. So first let me start with a very small example just to find the characteristic equation of a or characteristic polynomial of matrix. Find characteristic polynomial of following matrices. Okay, so what is the definition? How can we find the characteristic polynomial? What is the definition? Anyone?
Yeah, like if a minus lambda I determinant of that, if that is equal to 0.
Yeah. So, okay, we will equate to 0 if we want to find the root of the corresponding polynomial. Okay. So, what is the characteristic polynomial means? Determinant of, we can say, f of lambda equal to determinant of a minus lambda I. Usually, what we will write a polynomial means it is equal to some f of x equal to some a1x plus some a2x square plus something like this we will write. Okay, so polynomial means it is not equal to 0. When we will equate it equal to 0, at that time we will say it is the characteristic equation. Okay, characteristic polynomial means f of lambda equal to determinant of a minus lambda I, and the characteristic equation means determinant of a minus lambda I equal to 0. Determinant of a minus lambda I equal to 0. This is characteristic equation. That means we have an equality equal to 0. So this we will use to find the eigenvalues. Okay, when we equate to 0, what are all the roots of this characteristic or roots of the polynomial? That is the eigenvalues. Okay, now determinant of a minus lambda I means what is a? A is 2541. A is 2541, and lambda I means multiplying I with lambda, that is lambda 0 0 lambda. So what we need to find is determinant of A minus lambda I, that means determinant of the matrix A minus lambda I. So it will be determinant 2 minus lambda 5 4 1 minus lambda. So we can do the determinant as usual, 2 minus lambda into 1 minus lambda minus 20. So okay, yeah, I will write the lambda square minus 3 lambda minus 8. Okay, something like this we will get. So this is our characteristic polynomial. So if we are equating this to 0, and whatever the solution we are getting, we will get it as the eigenvalues. So eigenvalue question we will come later. And again for B also, B is for B, the characteristic polynomial is determinant of B minus lambda I. So B 1 minus lambda 2 3. See, whatever the minus lambda coming from diagonal, it is from the minus lambda I. So whatever the terms 1 2 3 3 0 4 6 4 5, that is our matrix B. So we can solve this, like we can find the determinant, and I think the solution is minus lambda cube plus 6 lambda square plus 35 lambda plus 38. Okay, you can just verify this. So this is nothing but just finding the determinant. That is why I am just going very quickly. If you have any doubt in this, or how to find the characteristic equation or polynomial, you can ask. Otherwise we can go to some other questions. Is this question okay for everyone? Okay, I hope it is okay for everyone. So let us go to the next problem. So in this problem, we will explicitly find all the eigenvalue, corresponding eigenvector, and whether it is diagonalizable, and so on. So now the question is A equal to 2213. First question, find all eigenvalues and corresponding eigenvectors. Is A diagonalizable? So we have already covered diagonalizable in the class, and if it is diagonalizable, find a matrix P such that P inverse AP equal to D, where D is diagonal. So this is the definition of diagonalizable matrix. If A is diagonalizable, we can say there exists a P such that, an invertible P such that P inverse AP equal to D. Okay, if that condition is satisfied, we will call A is a diagonalizable matrix. So here the question is to find, if it is diagonalizable, find the required P. And Next question is find a power 6. Okay, so after solving the first two part, finding a power 6 will become an easy task. So first of all, we will start with the characteristic equation. So here a is 2213, and what is determinant of a minus lambda I? This is 2 minus lambda, 2 1 minus lambda, sorry, 1 3 minus lambda, and this is 2 minus lambda. This is just the determinant, minus 2. So this is lambda square minus 5 lambda plus 4. Okay. So from this we can write it as lambda minus 1 into lambda minus 4. Okay. So what is our characteristic polynomial here? Characteristic polynomial we can say p of lambda equal to lambda square minus 5 lambda plus 4. Okay, polynomial means in terms of this. And what is characteristic equation? It should be the thing lambda square, that means the polynomial is equating to 0. Okay, now what are all the eigenvalue? Eigenvalue means solution of characteristic equation. That means the value of lambda which satisfy this characteristic equation. Okay, otherwise roots of characteristic polynomial, that means roots of this polynomial. Okay, now we already got that lambda square minus 5 lambda plus 4 is same as lambda minus 4 into lambda minus 1. That means lambda equal to 4, lambda equal to 1. So the roots are lambda equal to 4 or lambda equal to 1. So whatever we are obtaining as the root, this is the eigenvalues. Eigenvalues are lambda equal to 4 and lambda equal to 1. Now, okay, I just got the eigenvalue lambda equal to 4 and lambda equal to 1, and our matrix is a 2 by 2 matrix. Now, before finding the eigenvector and all, can you say whether this given matrix is diagonalizable or not? From this point, can you say?
No, we cannot say.
Okay, actually we can say from this point itself, because I got two distinct eigenvectors.
Okay.
Sorry, eigenvalues. Okay. Suppose if I got after this solution, I got lambda equal to 4, lambda 1 is 4, lambda 2 equal to 4. Both are same. At this point, I cannot say anything. I need to find the null space of a minus lambda I and all. Then only I can say. But at this point, if I have all the roots are or all the eigenvalues are distinct. Okay, if an n by n matrix I am getting n distinct eigenvalue, at that time we can say it is diagonalizable. Okay, okay, leave that. Before that, we will go to the eigenvector. How we will find the eigenvector?
We'll solve the homogeneous equation
Yeah,
keeping the
that is a minus lambda x equal to 0. This equation we will solve, correct, for corresponding to each of the obtained lambda. Here first we have lambda equal to 4. So what we will solve? A minus 4i x equal to 0. This equation we will solve. So yeah, our a minus lambda I was 2 minus lambda 2 1 3 minus lambda. So this was our A minus lambda I matrix. So A minus 4i means what we will get? Minus 2, 2, 1, minus 1. Okay. Into x1, x2 equal to 0, 0. So we need to solve this homogeneous equation to obtain the solution. Now, from this actually what we are getting is minus 2x1 plus 2x2 equal to 0 and the x1 minus x2 equal to 0. Actually both of these equations are same, right? One is a multiple of other. If I am multiplying first row with minus 2, sorry, second row with minus 2, I will obtain the first row, right? So,
Yeah.
so what we are getting is this is same as this implies x1 equal to x2. For if whatever I am giving the value to x2, I will obtain x1. That is only one free variable is there. So what is the eigenvector corresponding to lambda equal to 4? Any eigenvector?
1 1.
Yeah, 1 1. 1 1 is a 1 1 is an eigenvector corresponding to lambda equal to 4. Okay. Now, now we can say null space of A minus 4i. What is null space of A minus 4i?
It's 1.
Uh,
Sorry, it's
null
null.
space, yeah.
The last row will become 0. So null space.
Okay, first of all, does 1 1 belongs to null space of A minus 4i? Actually, what we are doing here, A minus 4i, see, whatever we are doing here is, we are finding the null space of A minus 4i, right? Okay. Okay, by definition, what is null space of A minus 4i? Set of all x such that A minus 4i of x equal to 0. This is the definition, like all the elements x such that it is mapped to 0 under A minus 4i. So, that is what we have found here. A minus 4i equal to 0. A minus 4i into x equal to 0. So, what should be the x? That is what we got, x1 equal to x2. Okay. So, if we are giving some particular value 1 to x2, then x1 should also equal to 1. So, 1 1 is a 1 1 belongs to null space of A minus 4i. Correct? Is that okay? So, this is equal to set of fold x times 1 1. That means the space generated by 1 1. It is not just 1 1. Set of all x times 1 1 such that x in R. Fine. Okay. So, the thing is, an element belongs to null space of A minus 4i. A non-zero element belongs to null space of A minus 4i is equivalent to saying that it is an eigenvector corresponding to 4. That is what we are saying here. Okay, here what we got, 1 1 is an eigenvector corresponding to lambda equal to 4. So, 1 1 is eigenvector corresponding to lambda equal to 4. So, what does, by definition, it says that 8 times 1 1 equal to lambda times lambda is 4, 4 times 1 1. So, if we are taking the 4 times 1 1 to left side, what we can say, A minus 4i of 1 1 equal to 0. Okay, that means what here says, it says 1 1 is an eigenvector and this says 1 1 belongs to null space of A minus 4i. Fine. So we got null space of A minus 4i is set of all. Other than 1 1, nothing will belong because we found all the solution of A minus 4i x equal to 0. So only 1 1 and its multiples are the solutions. So null space of A minus 4i contains all the linear combination of 1 1. Now Can you say what is the geometric multiplicity of 4? Geometric multiplicity of 4.
It's one.
Yeah. What is the definition of geometric multiplicity?
The nullity
Yeah.
of the A minus 4i matrix.
Nullity of matrix A minus 4, we can say. Okay. And okay, before that I should have asked what is algebraic multiplicity?
Mm, The number of times the root is
Yeah,
repeated.
number of times the root comes in the characteristic equation. So here it was only one time. It was like lambda minus 1 into lambda minus 4. So this is also 1. Okay.
Ma'am, one question. Can you please explain this lines which you have said above the null space and that it's a little bit not clear, this part.
Okay. Okay. See, what we are doing is first we are finding uh, an eigenvector corresponding to the eigenvalue lambda. Okay. So x is an eigenvector corresponding to lambda.
Yeah.
This is
Mm.
if and only if Ax equal to lambda x, correct?
Yes.
That means x is a non-zero vector. Okay, that's understood. So now Ax equal to lambda x, how I can write? A minus lambda I times x equal to 0.
Yes.
Okay.
Mm.
Now, what does this means? X belongs to
Mm.
null space of A minus lambda I.
Okay.
Okay.
So this line actually is not, this is the line which is not clear. So when we say null space, it
Hmm.
means how do we define null space? Say anything which is making the equation zero.
Yes.
Uh, but x is make in this case the value of x is 1 1, which is making it 0.
Hmm.
Uh, so so null space of ai a minus lambda I, um,
Okay. Let us see the definition of null space first.
yeah,
For a matrix, let us say it is B. Okay. B is a matrix. Then
okay,
what is null space of B? Set of all x, like x can be in Rn if B is a n by n matrix. Correct?
yeah,
Such that Bx equal to 0. Like what are all the elements x such that B is mapped to 0. Like
okay,
B into x is going to 0. If
mm,
T is a linear transformation, how we will write null space of T? Set of all x such that what are all x such that T is mapping to 0. Tx equal to 0, correct?
yeah,
This is same as this one. If T we are writing in a matrix form B or something, that is
okay,
null space of B. Now,
okay,
here instead of B, what I am having? A minus lambda I. That is also a matrix now, correct?
okay,
So,
yeah,
if B equal to A minus lambda I, null space of B will become null space of A minus lambda I. So, I am just substituting instead of B A minus lambda I x equal to 0. Okay.
yeah, I got this part, ma'am. So, like when we have this matrix and we reduce it to the reduced row echelon form,
Hmm.
one of the row becomes completely zero because we saw that
Hmm.
rows were identical.
Yes.
So now we from there I understood that one row is zero, so dimension of the rank is one and dimension of the null space is also one, right?
Yeah, correct.
And so nullity is one.
Yes.
Uh, so that part I understand, but deriving because using so deriving
Okay, this
uh,
step you are not able to understand.
yeah, yeah.
Okay. So, okay, from that way we can say nullity, like rank is 1. So, by rank nullity theorem, nullity should be equal to 1. Okay.
Yeah.
Now,
Mm.
by definition, what we are having is null space means set of all elements such that a minus 4i x equal to 0.
Yeah.
Okay. And uh, now what we can do is, okay, null space of a minus lambda, so a minus 4i equal to set of all x such that a minus 4i x equal to 0. Okay. Now
Yeah.
I am starting this condition a minus 4i x equal to 0. Okay.
Yeah.
I want to find, like, suppose I don't know the rank nullity theorem, I just know this is the null space.
Yeah.
Okay,
Good.
so I have only one condition a minus 4i x equal to 0. Now I am doing a minus 4i x equal to 0. So
And find,
what
yeah,
was
which
that? It was
value.
minus 2 to 1 minus 1.
Yes. Yes. Yeah, this calculation I understood. So
Yeah.
we finally find that x1, x2 is 1, 1, and that's when it will become 0.
Yeah, from this what we are getting,
Okay.
x1 equal to x2, and
I get it.
yeah, it should be in the form, so it should
Mm.
be in the form x into 1
Mm.
1. That is what I have written earlier.
Which makes the matrix 0 is belongs to the null space, I think.
Yes, only
Yeah.
1 1 and its multiples.
Yeah. Sorry
Okay,
for the digression here. Thank you.
it's okay.
Mm.
uh, yeah, so okay, we got the algebraic multiplicity is for algebraic multiplicity is the uh, how many number of times that particular 4 is the root of our characteristic polynomial, and the geometric multiplicity is the dimension of the a minus, like null space of a minus 4, right? Now in the same way, for lambda equal to 1 also we need to find. Okay, let us do that quickly. So a minus lambda I was 2 minus lambda 2, 1, 3 minus lambda. Okay. So lambda equal to 1. What we can say? Null space of a minus lambda I. Either this way we can do, otherwise we can do as earlier, like ax equal to lambda x, means this is the finding the eigenvector. Oh, this is also the same way. So let me see what is null space of a minus lambda I. This is set of all x such that a minus, here lambda is 1, a minus ix equal to 0. So this is nothing but set of all x such that here what is our matrix? A is 1 2 1 2, x1 x2 equal to 0. Okay, so here our condition is x1 plus 2x2 equal to 0. Here again both the equations are same. So from this, if I am substituting uh, x2 equal to 1, then x1 should be equal to minus 2. So minus 2 1. Okay, so minus 2 1 belongs to null space of a minus lambda I. So what does this means? A minus lambda I into minus 2 1. If I am multiplying the matrix a minus lambda I with the minus 2 1, I will get 0 0. So what does that means? A into minus 2 1 equal to, here lambda is 1, 1 times minus 2 1. So what we got? A non-zero vector x such that ax equal to lambda, ax equal to 1x. So here 1 is our lambda, x is minus 2 1. So in this way we can say minus 2 1 is an eigenvector corresponding to 1, and also we can say this span of minus 2 1 is the null space of a minus a. Okay, so this is exactly same as the lambda equal to 4 case. Now, here again, what is the geometric multiplicity? Can anyone say quickly?
Geometric multiplicity is 1.
Yeah, and algebraic
Yeah,
multiplicity?
also same.
Algebraic multiplicity also 1. So, from here we can say again it is diagonalizable, as already I told, corresponding to see, okay, here am of 4 equal to gm of 4 and am of 1 equal to gm of 1. Okay, algebraic multiplicity and geometric multiplicity are equal for each of the eigenvalue. So this condition actually implies A is diagonalizable. Okay, so okay, before reaching this, in the beginning itself I told, as we are having only two, definitely it is diagonalizable. So let us see why it is actually. Now, what was our equation? P of lambda equal to lambda minus 4 into lambda minus 1. So from here we got algebraic multiplicity equal to 4 and geometric multiplicity equal to, sorry, algebraic multiplicity of, okay, algebraic multiplicity of 4 is 1, algebraic multiplicity of 1 is also 1. Now, uh, one thing is, geometric multiplicity will be always less than or equal to algebraic multiplicity, and it will be always greater than or equal to 1. Okay, so this result is there even though uh, okay, this actually now you don't know why geometric multiplicity is less than algebraic multiplicity always. Here we can see why it is always, because corresponding to each eigenvector, sorry, eigenvalue, at least one eigenvector is there. Okay, that eigenvector will belongs to the null space of A minus lambda I. Okay, for each lambda which is an eigenvalue, there exists x such that Ax equal to lambda x. Okay, that implies this x belongs to null space of A minus lambda I, and dimension of null space of A minus lambda I is the geometric multiplicity of lambda. Correct? So it should be at least 1, because at least one non-zero x belongs to null space of A minus lambda I. So it should be at least 1. So that is the one here, geometric multiplicity greater than or equal to 1. Okay, this is a this result you can just remember, geometric multiplicity always will be less than or equal to am. So in the beginning we got am equal to 1 for both 4 and 1. So from here what is the only possibility? Gm of 1 should be equal to 1 and Gm of 4 should be equal to 1. Is that okay?
Yeah.
Yeah, so that is the reason I told, if we have distinct values, we can instantly say that is a diagonalizable matrix. Now, uh, how can we find P inverse? So now next question is to find the, sorry, P such that P inverse AP equal to D. Anyone knows how to find the P?
So, corresponding to each lambda,
Hmm.
we put the each vector, eigenvector in a column form
Yes.
to make the P.
Correct. So what we got is corresponding to 4 we got 1 1, and corresponding to 1 what we got minus 2 1. Okay. So how we will construct P is, if it is diagonalizable, the way of constructing P is we will write the corresponding eigenvector in column minus 2 1. Okay. From this we got P. Now find the P inverse, multiply with A and then with P, we will get a diagonal matrix. So now can you say what will be that diagonal matrix? For that also there is a like well defined form.
Yeah, so like since the first column is for 4, we can put 4 first.
Yeah.
then 0 and then 0 and 1.
Correct. Because this one is corresponding to 4. So if we are interchanging, like if P we have written as minus 2, 1, 1, 1. In this way, the corresponding D will be 1, 0, 0, 4. Like whatever it is diagonal only. So it just depends on the order how we are constructing the P. So you can just verify this also. Find the P inverse, multiply P inverse AP. So we will obtain this diagonal matrix. Okay. Now the last question was find A power 6. Okay. We know what is A. A is our 2213. Is this easy to find the A power 6? Very like we can do A into A into A into A like that. Other than that, what is the easy way to find the A power 6? Okay. What we are having is P inverse AP is a diagonal matrix. Now, any idea how can we proceed from this? Okay. Or what is A? From this, how can I write A?
A is equal to P, P D, uh, P inverse.
Correct. What I am doing is multiplying here with P, here with P inverse. Here also P inverse. Okay. So this P inverse will get cancelled. This will get cancelled. Means it will become identity. Okay. So here in the left side we will get just A, and right side we will get just P inverse. Okay. Okay. Now what is A power 6? That is P inverse power 6. Now what is this one? In the right hand side, what is this actually? We are multiplying P inverse. What is this? Okay, let me expand it. P inverse first time, P inverse second time, P inverse third time, etc. P inverse sixth time. Now, what is this? How can I simplify this term?
P into D raised to 6.
Yeah, because here whatever we are having P inverse P, this will become identity. This P inverse P will become identity. In the same way, up to all this value, like only D is remaining. All other P inverse, no, P inverse P will become identity. So we will remain with the first P, all the middle P inverse will become identity. And the first P and in the middle D power 6 and the last term P inverse. Okay. So we already know what is P and find the P inverse. What is the P inverse formula? Adjoint A by determinant of A. Okay. It's easy to verify. So find the P. What will be D power 6? D is 4001. Then what will be D power 6? D is diagonal matrix. That is why we are taking it to D to get the easy calculation. So it will be 4 power 6, 0, 0, 1 power 6, right? Okay, all other terms are 0. So we only need to multiply with the diagonal entries only. So this will be D power 6. So just multiply, just find the P inverse. I haven't found the P inverse. Okay, you can find the P inverse and multiply this term, and we will get the A power 6 like this. Fine. Find P inverse. So That is the way we can find the,
8 is to 6.
yeah. Now, okay, next question, true or false. Okay, we'll see some true or false question. If A is an n by n matrix and determinant of A equal to 0, then 0 is an eigenvalue of A. Is this true or false? Like given A is an n by n matrix and determinant of A is 0.
Ma'am, can we start? Like, I haven't thought about it, but we know that determinant of A minus lambda is 0.
Hmm.
So determinant of A minus, since it is like we can distribute it, so we can say determinant of A minus determinant of lambda I is equal to,
No, like determinant of A plus B is not equal to determinant of A plus determinant of B. Determinant of
okay,
A B is okay, determinant of A into determinant of B. But addition,
okay,
subtraction we cannot do.
okay, okay. Mhm.
Okay, what is this says? Determinant of A equal to 0. What we want to prove? 0 is an eigenvalue of A or 0 is not an eigenvalue of A. Okay, uh, no. Does the existence next belongs to null space of A? X non-zero. Okay, that is my first question. Does there exist a non-zero X belongs to null space of A? That is, does there exist a non-zero X such that Ax equal to 0? We already know that A into 0 equal to 0. That is correct, right? 0 is a trivial solution. Now, my question is, does there exist a non-zero solution for A? That is, does there exist a non-zero X such that Ax equal to 0?
Since A is already 0, so X can be anything, right?
No, A is not 0. Determinant of A is 0.
Okay, yeah.
Okay. Uh, okay, let me ask one question. Suppose A has only 0 solution. A 0 equal to 0 is the only solution. Okay. Now, is A is invertible for, are you getting what I'm
Yeah,
saying?
yeah. So if determinant of A is 0, it means it is not invertible.
Yeah, it is
Now,
not invertible, correct then?
so if Ax is equal to 0 and determinant of A is 0, uh, that means A is not invertible, so X has to be invertible, right?
X can be non-zero. Not X can be non-zero. There exists a non-zero X, correct? See, what
Yeah,
we are having is, uh, suppose X equal to 0 is only solution, correct? That means 0 is the only solution. That means rank of A, nullity equal to 0, correct? Because there is no non-zero solution, nullity is 0. That means A has rank n, full rank is there.
yeah,
What does that mean? A is invertible.
yeah. But that is not true.
That is not true because determinant of A is 0. So what does that means? There exists a non-zero solution, correct? That implies there exists a non-zero x such that Ax equal to 0. Are you getting?
Uh, Ma'am, why can't both be true? Like determinant of A is also 0 and X is also.
Yeah, it can be true. Okay. Determinant of A equal to 0. Whatever A I am giving you, you can take 0 as a solution. A0 equal to 0. So my question is there any non-zero solution? Because I want non-zero solution. Like what we are going to do, whether 0 is an eigenvalue. If it is an eigenvalue, what we want? A non-zero x such that Ax equal to 0x. Clear?
Yeah.
Okay, so okay, let me finish this. What we got? Ax equal to 0 with a non-zero x. What does that means? There exists a non-zero x such that Ax equal to 0x. Fine.
Yeah.
Now what does this means? This is just the definition of eigenvalue. That implies 0 is an eigenvalue. What is the definition of eigenvalue? There exists a non-zero x such that Ax equal to lambda x. Correct? Huh? So we got
Yeah.
a non-zero x such that Ax equal to 0x. Here 0 is the eigenvalue. That is what we are checking. Fine. So if determinant of A equal to 0, we have a non-zero solution for A. Okay. That non-zero solution means it belongs to the null space of A. It means that Ax equal to 0x. That means 0 is an eigenvalue. So the given statement is true. Is that okay for everyone? Any doubt? Okay, if anyone is having doubt, please ask. We can clarify and go. It is just like if you are writing like step by step, you will understand what is happening.
Ma'am, can you please explain it once again? Sorry, I'm not very clear.
Okay then. Yeah. So the given condition is determinant of A equal to 0. Okay. What is the question? Is 0 an eigenvalue?
Yeah.
When will you say 0 is an eigenvalue?
Yeah, I understood the part where you came to the point where Ax is equal to 0x, then 0 becomes a lambda, which is an eigenvalue.
Hmm.
But before that, how did you arrive till that line?
Okay,
That
so okay, we will start from back to front. Okay, so 0 is an eigenvalue means uh, there exists an x not equal to 0 such that Ax equal to 0x. Okay, that means we need to prove that Ax equal to 0 for some non-zero x. Correct? In order to prove this, we need to prove this. Now, does there exist a non-zero x like that? Okay. Now, what is the equation we are having here? Ax equal to 0. Now, this is a linear equation, homogeneous linear equation. We have already studied, like in the week 1 or 2, we have studied Ax equal to 0 A is an n by n matrix. So, it is an n equation in n unknowns.
Mhm.
Correct?
Yeah.
When will it have a unique solution?
When rank of A is complete, uh,
Yeah,
full.
rank A equal to n.
Yeah.
Correct? That
Yeah.
is the unique solution. So rank A equal to n means this is nothing but determinant of A is non-zero. Correct? No doubt, right?
Yes, it's not 0. Yeah.
Okay. Now, uh, infinite solution. We have only two cases for homogeneous. In that case, what is this? Rank of A is less than n, and in that case determinant of A equal to 0. This is also okay, right?
Yes.
So what is the case here?
Determinant of A is 0.
Second case. So what does
Yeah.
this mean? It has infinite solution.
Okay.
Okay,
Mm-hmm.
so
Yeah.
only zero solution is not possible. That goes to this case. Only zero solution means
Mm-hmm.
infinite solution means other than zero, so many solutions are there. So there exists at least one non-zero solution, correct?
Yes, yes.
So that non-zero solution we are taking, that x non-zero we are taking such that ax equal to 0.
Okay. Yeah.
Okay, so we got ax equal to lambda x form. So 0 is an eigenvalue.
Okay.
Okay, now let me ask the converse. What is the converse? Uh, if 0 is an eigenvalue, then determinant of A equal to 0. Is this true or not?
If 0 is an eigenvalue, then
Okay. Again,
yeah, that is also true, right?
yeah, correct. That is also true. How
Yeah.
we can write it? Now, what we can say, or
So, like, we can start with Ax is equal to 0x.
Ax equal to 0x because 0 is an eigenvalue.
Yeah. And since x is a uh, eigenvector,
Yeah, not equal to 0.
it's not
Eigenvalue.
equal to 0, so A is equal to 0.
Not a 0. What we can say, Ax equal to 0, Ax not equal to 0, and Ax equal to 0. Okay. So what should be rank of A?
Rank of A should be less than n.
Strictly less than n, because nullity is greater than n here, because a non-zero x belongs to null space of A,
Yeah.
so it should be greater than or equal to 1 n. So
Okay. So this
rank should
implies
be less than n. In that case, what should be determinant?
0.
Equal to 0. So simple. So both are
Okay.
like if and only if condition.
Okay.
Okay.
Yeah.
Yeah. Now the next question is, uh, every diagonal matrix is diagonalizable. Is this true?
So, like in this, D matrix is diagonal matrix,
Hmm.
and it has the eigenvalues in it. So, for finding diagonalizable,
Okay, what is the definition? Like basic definition of diagonalizability.
like what we did was like find the geometric multiplicity and arithmetic multiplicity, and if they are equal for each lambda,
Yeah.
then we said it is diagonalizable.
Okay. Actually, that are all methods to find whether a given matrix is diagonalizable or not. So the definition of diagonalizability is there exists a invertible P such that P inverse AP equal to D. This is the definition actually. Okay, so how to find this P and all? That is why we are going to eigenvalues, finding the eigenvector, finding the P, and then we are obtaining the D with the diagonal as eigenvalues, correct? So This is our definition. Just using this definition, think whether the diagonal matrix is diagonalizable or not. Means, can you find a P like that or not?
Mhm. So we can again multiply by pre-multiply by P and post-multiply by P inverse like that.
No, no. What should be that invertible P? So, see, what I am having is some diagonal matrix like this d1, d2, etc. dn. Here it's 0. Can you think about any invertible P such that P inverse A P is okay. Can you think about any P such that P inverse A P equal to A? A itself is a diagonal matrix. So instead of D, we can write it A. Correct?
Yeah, that's what I was thinking. Like if we can just move the P and P inverse on the right side, then uh,
Okay, what about identity? It
no,
should
no,
work,
I'm not.
right? So what is identity 1 1 etc. Along the diagonal, and here it is 0. Here along diagonal d1 to dn. Again, identity inverse and identity are both identity, correct? It should be equal to the matrix itself, right?
Mhm.
See, it's nothing like identity into A, I inverse A, I. What is I inverse? It is again I, A, I. Like if I am multiplying any matrix with a pre-multiply or post-multiply, whatever, what I will get? The same matrix. That
Mhm.
is A. Fine.
Mhm.
So that is our P inverse or P. P is the identity. Take P equal to identity. That's all. Simple. Fine. Okay.
So, like the question was like every diagonal matrix is diagonalizable.
Hmm.
So, is it that because we found one P, that means it will be diagonalizable?
Yeah, the only thing is to check the diagonalizability. If we are
Mhm.
able to find a P which satisfies this condition, then it is diagonalizable.
Mhm.
Okay,
Okay.
so in like very complicated, see, this is diagonal matrix, so that is why we are able to find like this. If some random matrix we are getting, arbitrary matrix we are getting, we don't know whether it is like how we will find P and all, correct? That is why we are finding the characteristic equation at its roots, eigenvector, like if the
Okay.
algebraic multiplicity equal to geometric multiplicity, then we will
Okay.
say diagonalizable, and yeah, whatever the procedure we will do. Here it is easy, that's why we are doing. Okay.
Okay.
Okay. Now the next question. Okay. This again symbol fx is an eigenvector corresponding to lambda. Then Cx is an eigenvector corresponding to eigenvalue lambda. Lambda is an eigenvalue and x is an eigenvector corresponding to lambda. Then what about Cx? Any idea? C is non-zero. Let us see.
X is
See, only thing if C equal to 0, what will happen? Cx equal to 0. Then we cannot say it is an eigenvector, correct? Eigenvector means a non-zero x such that Ax equal to lambda x. Okay, that is why I am excluding the case C equal to 0 case. Now, when we will say Cx is an eigenvector of lambda corresponding to lambda? Definition. So some matrix A is there. Okay. Okay. X is an eigenvector corresponding to lambda. That is Ax equal to lambda x, x non-zero, x is a non-zero vector. Okay. Now apply the same definition for Cx. What we will get? Acx should be equal to lambda times Cx. Instead of x, I am giving Cx. If this is satisfied, Cx is an eigenvector. Because x is non-zero, C is non-zero, Cx is non-zero. So Acx equal to lambda times Cx, then it is a eigenvector. Now, what is A times Cx? The only thing we know is Ax equal to lambda x. And we need to reach to this condition. How can I write A into Cx?
We can pull C.
Yeah, C times Ax, right?
Yeah.
Now, what is Ax? Ax is lambda x from the already known condition. Ax is lambda x. Again, lambda and c are just constants. I am taking lambda here and cx together. So what I got? A cx equal to lambda times cx with the cx non-zero. So cx is also an eigenvector.
So, ma'am, this means whatever eigenvectors we find, if we keep on like multiplying them with constants, we'll get so like many eigenvectors, right?
Yes, yes, we will get. That means actually the eigenvector, uh, yeah, the span of the eigenvector is actually a like subspace.
Okay, that's like
Okay.
infinite.
Yeah, many we can find, like whatever the constant we are multiplying, we can get infinite number we will get.
Hmm.
Okay, now again, okay, next question. Again, addition we can check. X1, X2 are distinct eigenvector. If they are equal, what we will get? X1 plus X2 is 2 times X1, something like that. Okay, so I am taking these are distinct eigenvectors corresponding to lambda. Then X1 plus X2 is also an eigenvector corresponding to lambda. Okay. So how, like it is just like the earlier case. How we should write this? What we need
What
to prove? A into
A
x1 plus x2.
one, yeah, x1 plus x2 and
This is
x2.
what we need to check, right? Okay.
Yeah,
So we will start with the a x1 plus x2. How we can write this? We can split
A
it. Ax1 plus ax2. Now what is the ax1?
lambda x1.
Lambda x1 plus lambda x2. That means lambda into x1 plus x2. Okay, here for safety we can give x1 not equal to minus x2 also. Sorry. Okay, if x1 minus x2, like if x1 equal to minus x2, then x1 plus x2 will become 0. So, okay, just we will avoid that case. So, we will get this condition a x1 plus x2 equal to lambda into x1 plus x2. That implies x1 plus x2 is a an eigenvector. So what exactly it says is, if we are taking all the eigenvectors, then the linear combination also an eigenvector. So it means the span of the eigenvector forms a vector space. Span of eigenvectors corresponding to some particular value. Corresponding to eigenvalue lambda forms a subspace actually. Means it is closed under addition and scalar multiplication. Okay, that is what we proved here. So it is a subspace. So, okay. Okay, now the next question is, if x1 is an eigenvector corresponding to lambda 1 and x2 is an eigenvector corresponding to lambda 2. That means lambda 1, lambda 2 are distinct eigenvalues and x1, x2 are the eigenvector corresponding to lambda 1 and lambda 2. Now the question is whether x1 plus x2 is an eigenvector. Now I am not saying x1 plus x2 is an eigenvector corresponding to lambda 1 or corresponding to lambda 2. It can be lambda 1, it can be lambda 2, or it can be like any other some lambda or something. Okay. So, is this true always? What is the guess at least?
Like in the first glance, it looks like it will be true, but may not happen.
Yeah, it need not be true actually.
Okay.
Okay, so let me start with one example. A equal to 1001. So, what is the eigenvalues for this matrix? Just by inspection. Just looking at this, you can say. This is a
Mm.
diagonal matrix, right?
Yeah.
Yeah. So for diagonal matrix, what are all the eigenvalues? Just the diagonal entries. Okay, whatever the diagonal matrix I am taking.
Actually, this is 1000, right? Right now.
Yes, yes.
Okay, so
Uh, huh.
diagonal matrix, like, okay, so even zero can be a part of it. Yeah.
Yeah, it can be anything. Non-diagonal should be 0, that's all.
Mm.
In diagonal, whatever is okay. So, if I am considering determinant of a minus lambda I, what I will get? d1 minus lambda, etc., dn minus lambda, all other terms 0. So, if we are finding determinant, what we will do? Just multiply the diagonal elements, that's all, right?
Yeah.
So, our equation will be d1 minus lambda to dn minus lambda equal to 0. So, what are all the solution for this equation? d1, d2, etc., dn. Okay. So, these are all the eigenvalues. Fine. So, for
Yeah.
diagonal matrix, the eigenvalues are the diagonal entries. Hmm?
Okay.
Now, here we got eigenvalues are 1 and 0. Okay. Now, corresponding to 1, okay, I am not going to find the, okay, suppose x1 is the eigenvector corresponding to 1. Okay, we can find also, otherwise, let me just do this. Corresponding to 0. Okay. Now, we need to check whether x1 plus x2 is an eigenvector corresponding to some lambda. Now, what we need to check? A x1 plus x2 equal to some lambda into x1 plus x2. Will it be true or not? That is what we want to find, right? Now, what is ax1 plus x2? Ax1 plus x2 is ax1 plus ax2. And x1 is an eigenvector corresponding to 1. So, what is ax1?
Lambda x.
Yeah, lambda is 1 here. So, this is 1x1. Fine. And the
Yeah.
ax2 equal to 0 times x2. Corresponding to 0 means it is 0. So, this should be equal to x1. Okay. Now, our question is this one. Ax1 plus x2 is lambda into x1 plus x2 or not? Now, what are all the possible eigenvalues here? 1 and 0 only. No other eigenvalues. Fine? Only
Yeah.
1 and 0. Now, if x1 plus x2 is an eigenvector, either it should be corresponding to 1 or it should be corresponding to 0. Now, if x1 plus x2 is an eigenvector corresponding to 1. So, what we should have uh, from star, what we will get? X1 should be equal to x1 plus x2. That implies x2 equal to 0. But it is a contradiction because x2 is an eigenvector we know, so it should be non-zero. Okay. Now the second case is if x1 plus x2 is an eigenvector corresponding to 0. So what we will get? X1 equal to 0 times x1 plus x2. That implies x1 equal to 0. This is again a contradiction. Correct? Because x1 is also an eigenvector. So it cannot be 0. Is that okay? So x1 plus x2 is not an eigenvector corresponding to 1 or corresponding to 0. So it is not an eigenvector. That implies x1 plus x2 is not an eigenvector. Clear? Any doubt in this question? See, you can, this is just like I have given in general. Actually, you can find particularly the value x1, x2 and you can add and you can do also. I mean, just as a counter example, uh, like this also you can do. Fine. Okay, now we have next question. Okay. If lambda 1 and lambda 2 are eigenvalues, then lambda 1 plus lambda 2 is also an eigenvalue. Is this true or false? Sum of eigenvalues. Okay, you
You know,
can, yeah,
no. Yeah.
no. Can you give any example?
No, I'm just, I can just tell how I was thinking. Like, I was thinking if the characteristic equation has some roots, then their sum may not be the root, right?
Yeah,
So,
that's all. Yeah, very good. Okay, for example, we can start with the identity itself. 1 0 0 1. What is the eigenvalue here?
eigenvalue 1.
Only 1 because it is a diagonal matrix as I told already. The only diagonal entries are the eigenvalue. So 1 is an eigenvalue, that means 2 times repeated. Correct?
Yeah.
So 1 plus 1 equal to 2, not an eigenvalue. That's all. Or you can take any matrix like distinct eigenvalue also we can take. Some diagonal matrix like this 1 0 0 2 we can take. So 1 2 are eigenvalue, 1 plus 2 equal to 3, not an eigenvalue. That's all. Okay. Okay. Now the next question. What is the maximum number of eigenvalues possible for an n by n matrix? Okay, for an n by n matrix, what is the maximum possible distinct eigenvalues? How many eigenvalues it can be?
N,
Yeah, of course n. So what is the reason?
because it will be the characteristic polynomial will be of the order n,
Hmm.
and maximum roots can be n.
Yeah. So what is eigenvalue? Eigenvalue is the root of the characteristic polynomial. Okay, eigenvalue is the root of characteristic polynomial. Its degree is n. So it can have maximum n roots. So either this all n can be distinct or all can be equal or some can be equal, some can be. So maximum distinct eigenvalues are n. Okay. Okay. Okay, so let me just give one example. Here we can say 1 0 0 1. Here we have only one eigenvalue. So this is a 2 by 2 matrix. Only actually we cannot say only one. It is actually repeating. But if we are considering distinct eigenvalues, only one distinct eigenvalue. And in case 1 0 0 0, we have two distinct eigenvalue which is same as the order. Okay. Now, is there any case with zero eigenvalue? We have got matrix 2 by 2 matrix with one eigenvalue and two eigenvalues. So, can it be any case with zero eigenvalue? Zero eigenvalue means zero is not that zero is eigenvalue, that is no eigenvalue.
So for odd order, there definitely will be one,
Hmm.
and for even, I'm not able to like think like why. Uh,
Yeah. Okay. So for odd order, that's good actually. For odd order, always we have one real solution. Now we will start with the 0 minus 1 1 0. Okay. Let us see what is determinant of a minus lambda I. That means minus lambda minus 1 1 minus lambda. This is nothing but lambda square plus 1. Okay. Now is lambda square plus 1 equal to 0? As a solution,
no real
yeah.
solution.
If we are considering the real field, it does not have a solution. Suppose our all study are just restricted to the real field, this equation does not have a solution. No solution in real field. That implies no eigenvalue. But it completely depends on where we are studying, like in which field we are. Okay, so but if we are having, but in complex field, what are all the eigenvalues here? Lambda square plus 1 equal to 0 means lambda is plus or minus I are eigenvalues. Okay, so actually whatever the polynomial we are having, we will have n solutions, like whether repeating or distinct, we will have n solution, but that n solution we can say it is coming from complex only, complex field only. Okay, if it is completely real, then only we can say it is a it has real eigenvalue or it is solvable in the real field. Okay, but in this case lambda square plus 1 does not have a solution or does not have an eigenvalue in the real field, but in complex it always, like whatever the characteristic equation, in complex we always have a solution. Okay, okay, that's just a note. Okay, now we will do. Okay, I think the characteristic finding the eigenvalue, algebraic multiplicity, all those are just calculation only. So I will do the other kind of questions. Okay, prove or disprove. If A is an invertible matrix, n by n matrix, uh, and lambda is an eigenvalue, then 1 by lambda is an eigenvalue of A inverse. Okay. So, any idea about this? Question is, okay. Is 1 by lambda is well defined here? Like when 1 by lambda is not defined, lambda equal to 0. Will lambda equal to 0 here? Is that possible?
No.
No, because A is invertible. We already proved that if A is invertible, if A is non-invertible, 0 is an eigenvalue, and if 0 is an eigenvalue, A is non-invertible. That means if A is invertible, 0 will not be an eigenvalue. So clearly lambda is a non-zero value since A invertible. Now the question is 1 by lambda is an eigenvalue of A inverse or not. So if 1 by lambda is an eigenvalue, what can you say about eigenvalue of A inverse? Then okay, what should be determinant of A inverse minus 1 by lambda I? Our question is 1 by lambda is an eigenvalue of A or not? What is determinant of A inverse minus 1 by lambda I? So my question is whether this determinant is 0 or non-zero. Okay. Okay, once again. Lambda is an eigenvalue of A, that implies Ax equal to lambda x for some non-zero x. What does this mean? A minus lambda x equal to 0 for some non-zero x. Now, what is determinant of A minus lambda I? This is what we were saying like for some previous questions also. Okay. if there exists a non-zero x such that a minus lambda x equal to 0, that x belongs to the null space of a minus lambda I. That means rank of a minus lambda I should be strictly less than n. So determinant of a minus lambda I is 0. Is this statement okay for everyone? Okay? Any doubt?
Yeah.
Okay. So the same way, if 1 by lambda is an eigenvalue of A inverse, what should be determinant of A inverse minus 1 by lambda I?
Yeah, I mean, if it is an eigenvalue, then it should be 0.
It should be 0. So our what we need to check, it is an eigenvalue of A inverse or not. So what we need to check whether determinant of A inverse minus 1 by lambda is 0 or not. If it is 0, it is eigenvalue. Otherwise, it is not eigenvalue, correct? So let me check what is determinant of A inverse minus 1 by lambda I. Now, we just know that determinant of A minus lambda I equal to 0. So from this, we should reach to in terms of A minus lambda I. So what I can do is I am taking A inverse outside. So here it is identity. Okay. And what should be the next term? A inverse, I am taking A inverse outside from 1 by lambda I. What is this? This I can be written as A inverse A. This I, if I am writing as A inverse A, okay, let me write it as one step then maybe. So this is determinant of A inverse minus 1 by lambda A inverse A. This is fine, right? Because I is A inverse A. Now what we can do? We are taking the A inverse outside. Here it is identity 1 by lambda into A. Okay, this step is clear, I hope. Now, determinant, I can split determinant of A inverse into determinant of I minus 1 by lambda A. Now, the only thing we know is determinant of A minus lambda equal to 0. How can I convert this? Like what term I should take outside so that it, it will have some A minus lambda term. A we are having here. So,
Yeah, 1 by lambda.
not just 1 by lambda, minus 1 by lambda we need to take, correct?
Okay.
Okay. So minus 1 by lambda we are taking. If we are taking a constant also outside of the determinant, it will become power n, correct? Minus 1 by lambda power n. Because it is an n by n matrix. So it will become determinant of A minus lambda I. Okay, here instead of 1, we are writing lambda into 1 by lambda, taking the minus 1 by lambda outside. So minus lambda remains. Now, what is this value? This is 0 because lambda is an eigenvalue. Okay, so the total will be 0. Fine. This implies 1 by lambda is an eigenvalue of A inverse. That's all. Clear for everyone? Any doubt? Anyone?
No, it's clear.
Okay. So next question. It's a very simple question. Suppose the characteristic polynomial of matrix is given by, so what is the size of A? The options are 5 by 6, 6 by 6, 6 by 5 and 5 by 5. Okay, so you can say very quickly what is the answer. So given,
6 by 6.
yeah, 6 by 6. So characteristic polynomial will have the degree n if A is an n by n matrix. So obviously A and C are false because how we are finding the characteristic polynomial? Finding the determinant. That means determinant is applicable for only square matrix. So A, C are clearly false. Now we will see what is the degree of P of lambda. Degree of P of lambda means 1 plus 2 plus 3. So corresponding to lambda minus 1 there is 1, then 2, 3. So total it is 6. So answer is B. Fine. Okay. If A is an idempotent matrix, what are all the possible eigenvalues? Okay, first of all, do you know what is idempotent matrix?
No, ma'am.
Okay. A is idempotent if A square equal to A. If the square of the matrix is the same matrix, then we will say it is idempotent. Okay, so this is the only definition we are using in the question. Okay, so question is what are all the possible uh, eigenvalues for this matrix? Okay, so any idea? Okay, so suppose lambda is an eigenvalue of A, then we can say there exists a non-zero x such that Ax equal to lambda x. Okay, now uh, what is a square x? How we will write a into ax, right? Now, what we can write from here? Instead of ax, we can substitute the
Lambda x.
lambda x. Okay, now we can take the lambda outside and ax. Again, what we can do? Instead of ax, we can substitute lambda x. So, lambda square x we will get. Okay, now what we are using? We are just using the matrix multiplication. We haven't used the idempotency. That means a square equal to a we haven't used. How can you use that? Using that, what you can say, what is a square x?
Some lambda 1x, like a different lambda, right?
No, no.
I'm just
See,
okay.
I am starting with an eigenvalue. Our question is, what can be that lambda? Okay, so that lambda, we need to examine what is that lambda, what it comes. Okay, here I am asking you to use the idempotency of A. That means A square equal to A. So what we can write? A square x equal to ax, right?
Yeah.
So in the first step, whatever we are doing is just the matrix multiplication. In the second step, whatever we are using is the idempotency. From this ax again, I can write it as lambda x. So the equation 1 and 2, the LHS are equal. So what we are getting is lambda square should be equal to lambda x. So our aim is to find the lambda. That is why we are writing in terms of lambdas. So from this we can write lambda square minus lambda times x equal to 0. Okay. Is x 0?
No.
No, because it is an eigenvector. So x is non-zero. So lambda square minus lambda x equal to 0 with the x non-zero. So what is lambda square minus lambda?
0.
It should be 0. That is lambda into lambda minus 1 equal to 0. That implies lambda equal to 0 or lambda equal to 1. So for any idempotent matrix, we have only two possibility, either lambda equal to 0 or lambda equal to 1. Okay. So actually this possibility can come uh, in any combination. So for example, if I am taking a equal to 1 0 0 1, clearly this is identity matrix, a square equal to a only. Okay. Here we have only lambda equal to 1 is the only eigenvalue. Okay, here 0 does not come. So we are saying the possibility. We are saying it will come definitely. That we are not saying. So we are saying the only possibility. So for example, if B equal to 0 matrix, here again A square is A only. But here 0 is the only eigenvalue. Okay. Now can you say any matrix C such that, sorry, this is B square equal to B, such that C square equal to C and lambda equal to 0 and 1 are eigenvalues. Any 2 by 2 matrix? You can think about the, yeah.
1 minus lambda, uh, that is minus
No, only possibilities are 1 and 0. So my question is an example which contains both 1 and 0 as eigenvalues.
1 0 0 0. I'm not
Yeah,
sure.
1 0 0 0. Clearly you can check C square will be equal to C only. Correct? Yeah. And lambda equal to 0. See, this is the diagonal elements 0 and 1. So it is the eigenvalues. Both are eigenvalues. Okay. So any combination is possible. Both 1, both 0 and 0 and 1. Both, anything is possible. Now let us do for the nilpotent matrix also. Okay. What are all the possible eigenvalues of nilpotent matrix? Okay. Can anyone say what is nilpotent matrix? Anyone knows?
No, ma'am.
Okay. If there exists some n in natural number such that a power n equal to 0. That is a power n is the 0 matrix. So such a matrix is called a nilpotent matrix. Okay. So we will do very quickly. We will do the possible eigenvalues for the nilpotent matrix. So if lambda is an eigenvalue of A, then there exists a non-zero x such that Ax equal to lambda x. Okay. Now what is a power n of x? The same way we can do the matrix multiplication. a power n minus 1 into ax. What is this? A power n minus 1 into lambda x. That is lambda power a power n minus 1 x. So this way we can repeat. So what will be the final answer?
Um, Lambda raised to n.
Yeah, lambda power lambda power n into x, right? Okay. Now what is this a power n x actually? By using nilpotency, what is a power n?
0.
0.
0 into x.
Yeah, that is 0 into x means 0, right?
Yeah.
So what we are getting? Lambda power n x equal to 0. So from these two equations, and x not 0. Correct?
Yeah.
So lambda power n should be equal to 0. That implies lambda is the 0. That means if any eigenvalue we are starting with a lambda, that lambda should be equal to 0. Correct? Hmm? So lambda equal to 0 is the only possible eigenvalue. Okay? Okay, I think then we can stop today. Uh, okay, all other questions are actually based on like find the characteristic, that are all just calculations. So I haven't done so the calculation type questions much. So anyhow, I think let us stop for today. If you don't have any other doubt.
This final exam, can you give some idea how the paper is like? How duration, number of questions, type of questions, those kind of thing?
I
Just
think it is just like objective. Even I don't know how it will be.
okay,
About that, I think you can. Uh, where you will usually mail that support.
okay,
Yeah, yeah. I think you can ask in the discourse whoever handling that. Forum is there, right? Where you are
yeah,
asking the questions. Yeah, it's better to ask there, so they will answer properly. I don't know much.
okay, fine.
Yeah. Okay.
Okay,
Okay then. Thank you. Let's stop and we'll meet next week.
yeah, bye.
Bye bye.